Hi, my name is Tyler, and I'm a mechanical engineering major.
Hi, my name is Susie, and I'm a mechanical engineering major.
Hi, my name is Winston, and I'm a mechanical engineering major.
Hello, my name is Andrew Saki, and I'm a mechanical engineering major.
Hello, my name is Brandon, and I'm a mechanical engineering major. For our reverse engineering project, we chose a bike bell. We chose Hector Salamanca as our character because he uses a bell to communicate his intentions, similar to what you use a bike bell for. He clicks his bell frequently with a lot of force, and this can be modeled as a cyclic load, which is why we chose Hector Salamanca.
Here we have our exploited view of our SolidWorks assembly. The cover on the bottom is the bell's backbone. It houses all the internal components and connects it to the bike handlebar. The user first exerts force onto the lever, which rotates the central gear. The central gear rotates the weights, which strike the top bell to make this sound. The top bell cover also acts as a protective cover for the internal components.
For stress analysis, we chose the lever as users exert dynamic loads on this part. This is the part which drives the other bell components. Stress equations. We first assume the lever is a straight solid beam. The user applies an arbitrary force F at the end of the lever. These are shear moment diagrams. And from this diagram, we can locate our critical cross-section at this point. At this critical point, maximum bending stress is 211.63 times the arbitrary force. The maximum shear stress is 59.88 times the arbitrary force at the center and 105.81 times the arbitrary force at the edge. Since shear is higher at the edge, we'll use this as our tau max critical point.
Static failure report and plot. We assumed that the material is ABS plastic since it's common in bike bells. Based on our research, we assumed the yield strength to be 30 megapascals, which is a conservative estimate. To obtain the magnitude of force required to move the lever, we applied a similar force on a scale using one finger. Our measurements are in inches, so we recalculated the maximum shear stress in pascals. For the maximum shear stress theory, we rearranged the equation tau max equals Sy over 2n to solve for the factor of safety. For the distortion energy theory, we first rearrange sigma prime equals Sy over n for the factor of safety. Then, we calculate sigma A, assuming sigma B equals 0, since there's only one principal stress. Once we get the values of sigma A and sigma B, we plug and chug for the value of sigma prime, then plug into our second equation for n. Our factor of safety turned out to be 4.57.
This is our cyclic stress pattern. As you see, our stress oscillates from 0 to 6.56 megapascals. From our previous calculations and material properties, we solved for sigma A, which is our alternating stress or stress amplitude, and sigma M, which is our mean stress. We got 3.28 megapascals for both sigma A and sigma M.
This is our sigma A and sigma M graph. Both of our cyclic loading conditions are underneath the Langer and Goodman lines, and this is why we can predict it can have an infinite life.
We assume the extreme working condition where Hector rolls over his bike bell with an arbitrary 750 newtons of force on the lever. Under these conditions, the current design would fail on the first cycle. Our proposed solution would be to increase the factor of safety by changing the lever material from ABS plastic to mild steel. The following properties of mild steel are shown here. We then recalculated several values to evaluate the factor of safety under these new conditions. Based on Goodman, we see that the factor of safety is 1.14, and Langer is 1.02.
For Castielagos theorem, we are assuming that the lever is a straight bar, and we're calculating the deflection at the end where F is applied, so where you're pushing the bike lever. There's no torsion or axial load on it, which makes the calculations a little bit easier. So we're just looking at the bending moment and the shear. First, we calculated the strain energy and solved for displacement using Castigliano's theorem. And using the properties of ABS plastic, we find that the displacement is 1.566 millimeters, or 0.06165 inches. My name is Tyler.
I'm Andrew.
I'm Winston.
I'm Brandon.
I'm Susie. See you next time.